Hello students. Now we are going to discuss some properties of the Bessel function. So in the last video we derived the Bessel function Gn of x equal to summation r equal to 0 to infinity minus 1 raised to r x by 2 raised to n plus 2r into 1 divided by gamma of n plus r plus 1 into r factorial. So this is the Bessel function we derived from the series solution of Bessel differential equation. Now we have some properties. So this is the one, j minus n of x equal to minus 1 raised to n into gn of x, where n is a positive integer. We are going to prove that j minus n of x equal to minus 1 raised to n into gn of x. Now by definition of the Bessel function we have jn of x equal to summation minus 1 raised to r x by 2 raised to n plus 2r into 1 divided by gamma of n plus r plus 1 into r factorial. Okay, so this is by Bessel function. Now in this result we take n equal to minus n. Okay, j minus n of x equal to summation minus 1 raised to r x by 2 raised to n as minus n plus 2r into 1 divided by gamma of minus n plus r plus 1 into r factorial. Now in equation 2, this gamma of minus n plus r plus 1 we put in the form of gamma of r minus n plus 1, we take as minus common, then we get plus n minus 1. Now this gamma function is in the form of gamma of minus k. So this minus k is one negative. This is a negative value. Gamma of the negative value is representing when we take r equal to 0. See, we have a summation from r equal to 0 to infinity. When you take r equal to 0 in this gamma function, r equal to 0, 0 minus of n minus 1. So that 0 is less than n minus 1. When 0 is less than n minus 1, we get a negative value that we represented as a minus k, gamma of minus k. Even when you take r equal to 1 now, 1 minus of n minus 1, this is again the negative value because 1 is also less than n minus 1. Similarly 2 is also less than n minus 1, 3, 4 and so on. For all other values of r we get in the form of gamma of minus k. That's a negative value we get in the gamma function. Then up to n minus 2, up to n minus 2, n minus 2 is also less than n minus 1. So therefore from 0 to n minus 2 we get the gamma function as a gamma of minus k. We get a negative value. And also for n minus 1, when we take r equal to 0, 1, 2, 3 so on up to n minus 2, we get the minus of that is gamma of minus k. Then the after n minus 2, the next value is n minus 1. When you take n minus 1, we get gamma of 0. Okay, so here this gamma of 0 is not defined, and also this gamma of minus k we have in the denominator. We get the value in the denominator for 0 to n minus 2. Okay, then 1 divided, so that value become infinity. So 1 by infinity is 0. So therefore what we get for all the values of r, that is from 0 to n minus 1, we cannot define the gamma function. So therefore what we do, after n minus 1, the next value of r is n. So therefore we are going to consider the value of r from n to infinity. Okay, so as we have here from r equal to 0 to infinity, for r equal to 0 to n minus 1, so which is not defined, we are getting the value as 0. Therefore we consider the value of r from n to infinity. Okay, the remaining terms are same. Now this minus n plus r, that is r minus n, r minus n we take as a substitution. Yes, so then from this r value is s plus n, so that we are going to substitute here. When r equal to n, here when r equal to n, s equal to 0. So therefore this equation 3 becomes summation. Now r value is what? R is, that is s, when r equal to n, s equal to 0. So here we get as s equal to 0 to infinity. Then minus 1 raised to what is r? S plus n, x by 2 minus n plus 2 into r is s plus n. So that is 2s plus 2n. Then 1 divided by gamma of r minus n. R minus n is s, we took s here, plus this 1. Okay, then r is s plus n factorial, and again that we write as summation s equal to 0 to infinity minus 1 raised to s plus n, then x by 2 2n minus n plus 2s, and the remaining term same. Now by property of the gamma function, that is we have gamma of s plus 1 equal to s factorial and s plus 1 factorial as a gamma of s plus n plus 1. So these are the basic properties of the gamma function that we are using here. Then this j minus n of x equal to summation minus 1 raised to s plus n, then x by 2 n plus 2s, and here we are using the gamma function property. 1 divided by gamma of s plus 1 is s factorial, then s plus n factorial is gamma of s plus n plus 1. Okay, we used a gamma function property. Now from this we take minus 1 raised to n outside the summation, minus 1 raised to n outside the summation, then this summation s equal to 0 to infinity, then we left minus 1 raised to s. Okay, then x by 2 raised to n plus 2s, then 1 divided by this gamma of n plus s plus 1 into s factorial. See, we are going to prove that j minus n of x equal to minus 1 raised to n into gn of x. We have minus 1 raised to n. Okay, this minus 1 raised to n we got, and this term summation s equal to 0 to infinity minus 1 raised to s x by 2 raised to n plus 2s into 1 divided by gamma of n plus s plus 1 into s factorial. You just compare this summation with this gn of x. Here in place of r we have yes, in place of r we have yes. Okay, so therefore it is again a Bessel function. Okay, therefore comparing with 1 we observe that the summation in the RHS is, means this one is gn of x. Okay, just it is just a change of a variable, that is r as a yes. Therefore j minus n of x equal to minus 1 raised to n, and this we can take as a jn of x. Okay, so this is the one property. Now we take the second property, which is given by jn of minus x equal to minus 1 raised to n into jn of x, and this also we can take as j minus n of x, where n is a positive integer. Now taking the Bessel function jn of x equal to, okay, then in this Bessel function we take x equal to minus x. Okay, as by the result we take x equal to minus x, summation minus 1 raised to r x as minus x by 2 raised to n plus 2r, and this term as it is. Then summation minus 1 raised to r, this minus I am going to separate, minus raised to n plus 2r, that we can write separately, minus 1 raised to n plus 2r, taking minus term separately, then remaining x by 2 raised to n plus 2r and this term as it is. Now I take this minus 1 raised to n outside the summation, this minus 1 raised to n, then summation what left? Minus 1 raised to r into minus 1 raised to 2r. So minus 1 raised to r and minus 1 raised to 2r. So that is, we get minus 1 raised to 3r. That minus 1 raised to 3r we can write as minus 1 raised to 3, that whole raised to r we can write. Okay, this is what I have written. Minus 1 raised to r minus 1 raised to 2r is minus 1 raised to 3r, adding the power r plus 2r 3r, and again this we can write as minus 1 raised to 3 raised to r. So this minus 1 raised to 3, this is what I wrote here, raised to r, and the remaining terms same. Then this minus 1 raised to n summation, and this minus 1 raised to 3 is again minus 1. Okay, minus 1 raised to 3 is the odd power, it becomes again minus to the power r, then these terms same. Okay, thus Jn of minus x equal to this minus 1 raised to n. So again this is by definition of the Bessel function, we can write as Gn of x. Okay, and also from the previous property we have minus 1 raised to n into Gn of x equal to j minus n of x. Just in the a previous result we discussed this one, and we are using this property here. So Jn of minus x equal to minus 1 raised to n into Gn of x, and minus 1 raised to Gn of x is j minus n of x. Okay, so this is the second property of the Bessel function. And similarly, with the help of the Bessel function, we have some problems, some examples we have. With the help of the Bessel function, we are going to prove these results. Okay, then these are the important problems. Now, the first result is j half of x equal to square root of 2 divided by pi x into sin x. This is the one result we are going to prove. And the second result is j minus 1 by 2 of x equal to square root of 2 divided by pi x into cos x. Okay, so what we do in the Bessel function Jn of x, so once we take n equal to 1 by 2, we prove this result. Second, we take n equal to minus 1 by 2, we are going to prove this result. Okay, now, so here is the Bessel function. So as I said, for the first result, we take n equal to 1 by 2 in the Bessel function. Okay, j 1 by 2 of x equal to summation minus 1 raised to r x by 2 raised to n is 1 by 2. Okay, plus 2r and into 1 divided by gamma of this r, n is 1 by 2. 1 by 2 plus 1 is 3 by 2 into r factorial. Okay, then x by 2 raised to 1 by 2 I put outside the summation. So here I am considering only function of r, because we have a summation r equal to 0 to infinity. So I keep this x by 2 raised to 1 by 2, that is square root of x by 2, keeping outside the summation. Then this summation minus 1 raised to r, what left? X by 2 raised to 2r, and this term same. Now I'm going to expand this summation. Okay, so this is square root of x by 2 as it is. Now putting r equal to 0, wherever r is there we put r equal to 0. Minus 1 raised to 0 is 1, x by 2 raised to 0 is 1, then 1 divided by gamma of 3 by 2 plus 0. Okay, we get 1 divided by gamma 3 by 2, and 0 factorial is also 1. Next we take r equal to 1, minus 1 raised to 1 minus here x by 2 raised to 2 into 1 2, and this is 1 divided by gamma of 3 by 2 plus 1, that is gamma 5 by 2 into 1, r is 1 factorial. Then taking r equal to 2, minus 1 raised to 2 is plus then x by 2 raised to 2 into 2 4, 1 divided by gamma of 3 by 2 plus 2, that is gamma of 7 by 2 into r is 2 factorial. Okay, now we are going to use the gamma function. we have the results. Gamma 1 by 2 is a root pi. The value of the gamma 1 by 2 is root pi. And also we have a result, gamma of n equal to n minus 1 into gamma n minus 1. Okay. Now we are going to find the gamma 3 by 2, gamma 5 by 2 and gamma 7 by 2 using this result. Okay. When n equal to 3 by 2 in this, okay, 3 by 2. So here I write, just I do one problem. Gamma 3 by 2. Gamma 3 by 2 using the formula n minus 1 into gamma n minus 1. N is 3 by 2. 3 by 2 minus 1, 1 by 2 into gamma of n minus 1, that is 3 by 2 minus 1 is 1 by 2. So gamma 1 by 2 is root pi divided by 2. This is a gamma of 3 by 2 is root pi by 2. Similarly, in this formula, we take n equal to 5 by 2. When n equal to 5 by 2 and simplification, we get 3 into root pi by 4. Similarly, gamma of 7 by 2 we get as a 15 into root pi by root pi by 8. So these three values we are going to substitute in equation 2. Now, when we substitute the values in equation 2, we get jn of x equal to square root of x by 2, okay, as it is. Then substituting all the values. Then here from all the terms I take 1 divided by root pi as a common, and that root pi we take inside this square root of x by 2. Then here we left 2 minus x square, 4 cancel. We took this root pi common, so we left x square by 3 plus then this root pi we took common, 8 ones are 8 twos are 2 into 2 4, 4 into 15, that is 60. Okay, x raised to 4 by 60 and so on. Then what we do to get the required result from this series, we take 2 by x as a common. When we take 2 as a common here and also divided by x, we get x here minus, when we take 1 by x as common, so here we get x cube. When we take 2 as common, 2 into 3, that is 6 we get, plus when we take 1 by x as common, it becomes x raised to 5. Then we take 2 common, means this becomes 120. When you multiply this 2 by x, we get this term, these terms. Okay, then root 2 divided by root 2 is root 2. Root x by x is 1 divided by root x, so that we can write as square root of 2 divided by pi x. Then x minus x cube divided by 6 we can write as a 3 factorial plus x raised to 5, 120 is 5 factorial. Okay, now so we know this is one of the standard infinite series which is given by sin x. Therefore, j 1 by 2 of x equal to the square root of 2 divided by pi x into, this is the series for sin x. So this is the first result. Then to prove the second result, we take n equal to minus 1 by 2 in the Bessel function. J minus 1 by 2 of x equal to summation minus 1 raised to r x by 2. N is minus 1 by 2 plus 2r, and this is 1 divided by gamma of r plus that we have n plus 1. N is minus 1 by 2 plus 1. Minus 1 by 2 plus 1 is 1 by 2 into r factorial. Now I take again x by 2 raised to minus 1 by 2 outside the summation. Then summation minus 1 raised to r, x by 2 raised to 2r. Then this term as it is. Now again we are going to expand this summation. So this x by 2 raised to minus 1 by 2, taking the reciprocal, and that we can write as square root of 2 by x. Then putting r equal to 0, this is 1, even this become 1. Then 1 divided by r is 0, so gamma 1 by 2 minus, when r equal to 1 we get minus here. Then x by 2 raised to 2 into 1, 2. 1 divided by r is 1. 1 plus 1 by 2 is 3 by 2 into 1 factorial. When r equal to 2, minus 1 raised to 2, that is plus. Then x by 2 raised to 2 into 2, 4. 1 divided by 2 plus 1 by 2 is gamma 5 by 2 into 2 factorial. Similarly, as in the previous we discussed the values of the gamma function, again we use the formula gamma n equal to n minus 1 into gamma n minus 1, we find these values, and even in the previous also we found these values. Then square root of 2 by x, 1 divided by gamma 1 by 2 is root pi minus x square by 4. Then the value of gamma 3 by 2 is root pi by 2, that we can write as 2 divided by root pi plus x raised to 4 by 2 raised to 4 16. Again the value of gamma 5 by 2 we substituted here, and 2 factorial is 2. Now from this, from all the terms we take 1 divided by root pi as a common, and writing inside this square root 1 divided by 2 in divided by pi x, and here we get 1 minus 2 ones are 2 twos are x square divided by 2, that we write as a 2 factorial plus 4 ones are 4 fours are 4 into 2 8, 8 into 3 24, that we can write as a 4 factorial. Now j minus 1 by 2 of x equal to square root of 2 divided by pi x, and this is the series for cos x. So this is the second required result. Okay, thank you.